So for piecewise functions, what we have is we will have a set of rules and a set of functions. So basically, each run will say kind of rule 1. We'll have rule 2. So on and so forth. We can have rule 3, 4, 5, whatever. And then after it, what we do is we have these ifs. These tell us when to use that rule. So we are going to, if I read this first one, we are going to graph x plus 2 when, only if x is less than or equal to 0. We are going to use, see, 1/2 x squared when, only if x is greater than 0. So we end up graphing two separate functions, and each one we only keep a piece because we restrict the x values when we graph it, okay? So we'll kind of have our rule, and then we'll have when we use that rule, okay? So to give an example, we graph x plus 2, or we use this rule, only if x is less than or equal to 0. So our first one says, what is f of -3? Is -3 less than or equal to 0 or greater than 0? Well, because it is less than 0, because it fits this rule, it matches this rule. If x is less than or equal to 0, which -3 is, then we use this rule. So what do we do with that? Well, we say, well, f of -3, which rule do we use? X plus 2, we plug that in. So -3 plus 2 gives me -1. Why don't we use the other rule? Well, because x equals -3. And we only use that rule if x is less than or equal to 0. Our next one is f of 0. Well, f of 0, that includes less than or equal to. So that is also one of our green rules. So for B, right, which rule do we use? Well, f of 0, we use again x plus 2. That means 0 plus 2 is 2. On C, we have f of 3. Well, this time, f of 3 is greater than 0. So we use what rule? The 1/2 x squared. I don't plug it into both, we only plug it into one or the other, depending on if it meets these requirements. So 1/2 times 3 squared, 1/2 times 9, about 9/2. What does this look like if we graph it? Well, we're going to have two different sets of rules. This will match the graph x plus 2, so I can graph a y-intercept of 2, a slope of 1. But this is not the entire function, because we only keep this when what? When x is greater than 0 or less than 0. So we only keep where it is less than or equal to 0. So we erase all the rest of it. We only keep the piece that fits that rule when it's less than or equal to 0. What happens at greater than 0? Well, it says graph 1/2 x squared. What does that look like? Well, 1/2 x squared, if I plug in a 0, gives me 0. 1 gives me 1/2. 2 squared is 4. Half of 4 gives us 2. This is a parabola opening upward. But we don't keep both sides. We don't keep the whole parabola. We only keep where it's what? Greater than 0. We only keep that right side. The only other thing this is missing is because this is greater than 0, there's not an equal to there, then I need to go here and I need to just make sure at 0 that is an open dot. And that's how you would graph a piecewise function. This is something I want you to work on through the homework. We will be playing with piecewise functions on the test, but I'm not testing you on this specifically. This is one of the topics we're introducing, but you will not be tested on at this point. Either way, let's kick it up a notch and see how this works. So again, we will have a rule and we'll know when do I use it. Rule and when. This one's a little harder because what? It has 3 different rules. So we're going to start where x is less than or equal to 2. So anywhere less than or equal to 2, we will use the graph x plus 1. X plus 1 has a y-intercept of 1, a slope of 1. This is the entire graph there, right? But we don't keep all of it. We only keep what section? Less than or equal to 2. Let me get that second point a little clearer. So we only keep this portion of the graph. The rest of it, we erase. It had an equal to, so I'm leaving that as a solid dot. Then it says graph 3. What the heck does 3 mean? Basically like y equals 3. That is a horizontal line at 1, 2, 3. Okay? But we don't keep the whole graph. What do we keep? Between 2 and 4. So from 2, open dot. Well, it's really closed by the previous one, so that's fine. Because this crossed right here at 1, 2, yeah, at 3. So this open dot gets filled in by the solid dot on the yellow there. But we graph this between 2, 3, and 4. And at 4, closed dot. Our last rule says what? Negative 2x plus 7 if x is greater than 4. So we are on our third section. This went from here to here. And last, negative 2x plus 7. You got a couple options. I can go 1, 2, 3, 4, 5, 6, 7. Go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. I keep doing this until I finally get to down 2 over. These are all points along this line, right? But we only keep greater than 4. So 1, 2, 3, 4. That graph starts here and goes greater than. So that would be, let's see, how about blue? Okay, 3 different pieces. We don't keep the entire functions. It's basically, I mean, if I did the whole first function, the whole second function, and the whole third function, that's what it would look like. But we don't keep all of it. We only keep the pieces that fit in these regions right here. What is the domain? We didn't really talk about this. The domain, and I would say the range. So our domain, right? X goes left forever. Trace it from there. Here it stops. But is it open? No, it's open down here, but it's filled in up here. So it continues between those. If both of these were open, or if there was a gap, we'd have to put a gap in the domain. But it's closed here, and it picks right back up here, and it keeps going what? Right forever. So from negative infinity to infinity. If there's no gaps, we say the domain is continuous. If I was to talk about the range, that would be the ups and downs. Well, it goes down forever. Any gaps? Well, it goes up, jumps back down, but this isn't a gap because really the y value existed over here. It jumped here, went down here. All the y values, all the up and down, everywhere up and down, the y values are defined. So it would also be negative infinity to infinity. And both are continuous. This one, going left forever, so our domain would be negative infinity. From there, going right, there was a gap, but it got filled in, right? Keep going. this is solid. So even though there's a gap down here, x is still defined at 1, 2, 3. At x equals 4, the graph still exists. And then past 4, it continues to exist. The domain, this domain, is also continuous. What would not continuous look like? Well, there'd be a gap, right? Now the range definitely goes down forever. But when it goes up, it reaches a peak at 1, 2, 3. So the peak there is at 3. I don't need to do this separate domain because that's, again, going down forever. I don't care that there's a gap here because the y value is defined over on the left side. So this would be our range at the 3. Can it equal 3? Both of these are solid. Put a bracket there. What formula would make this piecewise function? Well, both of these are linear lines, so this equation right here is y is equal to m. Our slope looks like it's 1 over 1, so 1x plus our b, the y-intercept would be 0. So basically, this is y equals x. That's this line right here. Our second line, well, it starts here, but really, remember I'm doing y equals mx plus b. So this time the slope is down 1, right 1. So negative 1x. And the y-intercept, if I keep tracking this backwards, would have been at 3. And that would be this line right here. So what is the equation going to be? Well, it's going to be a set of functions. And we'll do f of x is equal to 2 sets of rules. First one is x. The second one is negative x plus 3. When do we graph this? When do we graph this? Well, how about from negative infinity up to and including 1. So how do I write that? If x is less than or equal to 1. Y equal to, solid dot at that 1 is still on the 1. When do we graph negative x plus 3? Well, that graph starts where? Starts at the 1, but not including the 1. So that's when, if x is greater than, but not equal to, the 1. So that's an overview of the topics to this section. More or less, I'm just wanting to introduce the idea of piecewise functions. For this course, I'm not going to be having you graph a bunch of these, but just kind of get used to these in the homework, get the idea of domain and range. That will be a big deal on the test, and keep up the hard work.